So, starting from where we left in our last class, a basic discussion on center of mass where I told you what really this center of mass business is all about. I said it's supposed to be a representation for a collection of particles, discrete or continuous, for the sake of applying Newton's second law to that collection. Right? I mean, it's a notional particle having a mass equal to the sum of the masses and having an acceleration promoted by F net external is mass into a certain acceleration which would be deemed as the acceleration of that notional particle, right? That's the center of mass particle. I also told you that we could compute the center of mass for a discrete collection and for a continuous collection. Did I speak about how we could do that for a continuous collection? Right? Bunch of dm's, r dm into r divided by some integral dm, etc. Right? Okay. Now, we would very quickly look into the basics of how we normally go about computing the position of the center of mass for various geometries, continuous geometries. For discrete point particles, it's nothing at all, summation mi ri by summation mi and so on. But for a continuous distribution, let's see how we could go about computing the position of the center of mass. If it's a symmetric distribution of mass, then its center of mass from symmetry considerations is going to lie at its geometrical center. If you have a uniform circular ring, then its center of mass would be at the center of the circle. If you have a uniform sphere, its center of hollow or solid, its center of mass is going to be at its geometrical center. If you have a uniform bar of a certain length, then its center of mass is going to be at its midpoint. If you have a square lamina, then its center of mass is going to be the intersection of the diagonals. Same with the rectangular. So then, when it's not exactly like this, where there is symmetry, but then not symmetry to this extent that the center of mass would lie at its geometrical center, then we need to figure out how to arrive at the position of the center of mass for some geometry. So it's not possible for us to take up every single kind of geometry in the class and deal with it, but let's say some basic geometries that we can deal with for the sake of computation of the center of mass. Now, in the first place, let's look at non-uniform bar of length L. Non-uniform bar of length L. When I say non-uniform bar of length L, well, a uniform bar of length L would have its center of mass at the geometrical center. But when it's a non-uniform bar of a certain length L, this is a certain bar. Now, when I look at a uniform bar of length L, then what it really means is that if I select one unit length anywhere on the bar, then that length will have the same mass everywhere, right? That means the mass per unit length would be the same at every point along the bar. That's a uniform bar. But a non-uniform bar would not subscribe to this condition. It's going to have a variable mass per unit length depending on where that length is selected, right? So now I'm talking of a non-uniform bar of length L, in which the lambda represents mass per unit length. Let's say this is x equal to 0, this is the x direction, and this is x equal to L, where lambda is a function of x. Lambda is the mass per unit length. What it really means is that if at a certain x, I select a small length dx. That means the ends of this shaded portion would be x and x plus dx. So if at x, I select around x a small length dx, then the mass of this is going to be lambda at x into dx. Mass per unit length into the length dx. Since this dx is very small, the mass per unit length at x is the same almost everywhere along this shaded portion. Right? Now, the one more thing, that the center of mass of this bar, again from symmetry considerations, would lie along the x-axis. So all that we need to do is compute the x-coordinate of the center of mass of this bar. Compute the x-coordinate of the center of mass of this bar. So the objective then is to be able to take a mass element dm into the x-coordinate of that mass element, sum up all the dm into x's by selecting suitable limits of the integral divided by the total mass of the rod. Right? Let me look at this element. What's the mass of this element dm? Lambda is the mass per unit length at x into the length dx. That's the mass of the shaded portion. That's the mass of the shaded portion, yes or no? Right? Are you there with me? Into the x coordinate of this dm. The x coordinate of this is x. So mi xi for this mass element. This mass element into the x coordinate of this mass element. We need to sum up all the mix's. Summing up all the mix's would really mean this integral, where x runs from 0 to L, right? That's the sum of all the mix's divided by the total mass. What's the mass of this? The mass of this is lambda x into dx is the mass of this. The mass per unit length at x is lambda x, lambda a function of x. This is lambda a function of x, mass per unit length, different for different values of x. That's why it's a non-uniform rod. In a uniform rod, the mass per unit length will be independent of x. It will be the same for all positions of the rod, right? Sum of all of this, where x runs from 0 to L. Summation mixi divided by summation mi, that's going to give me the x coordinate of the center of mass. If it's a uniform rod, then this lambda would come out. It's independent of x. This lambda would come out, and the two lambdas would cancel each other, right? And it will come, the center of mass would be at the midpoint of the rod, Now, this, of course, somebody would have to tell you what's the extent of non-uniformity in the rod. That means somebody might end up telling you, let's say, lambda at x is like a ax plus b. A and b are constant. All that you need to do then is plug in lambda equal to ax plus b and integrate with suitable limits. And you would be able to integrate this and arrive at the x coordinate of the center of mass of this, right? So that's like one linear distribution. This is a non-uniform linear distribution along a rod. And you can arrive at the x coordinate of the center of mass of the rod, right? Next, let me look at a uniform semicircular wire. Of radius r and mass m. Uniform semicircular wire of radius r and mass m. We'll attempt to find the center of mass for such an entity. This is a wire whose geometrical center is O, and obviously this is the line of symmetry, isn't it? This is for a uniform wire, for a uniform semicircular wire, this is the line of symmetry. There is no way to distinguish between points on the wire to the right of this line and points on the wire to the left of this line. There is no way to distinguish. And if there is no way to distinguish, nature will offer impartiality towards this lack of distinction between the two regions, one on the left and the other one on the right of this wire. Because, so for sure, the center of mass of this unit must lie along the line of symmetry, must lie along this line of symmetry. Somewhere along the line of symmetry, the center of mass of this must lie, right? Let me call the line of symmetry as the y-axis. Let me call the line of symmetry as the y-axis, and this is the origin. So the center of mass would have a y-coordinate, which is ycm. It would be ycm. What I then do is, now there are different mass elements along the wire. There are different mass elements along the wire, and different mass elements have different y-coordinates. I select a mass element into the y-coordinate of the mass element, and I do that for all the mass elements that cover the semicircular wire, that are included in the semicircular wire, and divide by the total mass of the wire. That will give me the y of the center of mass of this semicircular wire, right? So then a scheme for, first of all, locating a certain mass element. Okay. Realize that this theta would locate different mass elements. Theta equal to 0 will locate a mass element here. Theta equal to pi will locate a mass element here. So if theta becomes our subject of summation, then theta running from 0 to pi would include all mass elements along the semicircular wire. Theta equal to 0 to pi would include all mass elements along the semicircular wire. So that will become our scheme for the required summation, right? Okay. Well, we are going to select small elements along the wire at a time. Small elements along the wire. One thing, there is mass distributed along a length, which is the circumference, right? What's the total mass? M. Distributed over what length? Half the circumference, that is pi r by 2. So mass per unit length is m by pi r by 2. That is 2m by pi r. That's the mass per unit length. Oh, I'm so sorry. M by pi r. I'm so sorry about m by pi r. M by pi r. I'm so sorry about it. So mass per unit length, m by pi r. Now, what I do is, I select a small mass element here. This is the small mass element that I select here. Small mass element that I select. This small mass element subtends a small angle d theta at the center. Subtends a small angle d theta at the center, right? The length of this mass element is r d theta. Do you realize that? The length of this mass element is r d theta. So the mass of this element would be mass per unit length into length. So the mass of this element is going to be lambda, mass per unit length into the length. That's a mass for the element into the y of the element. Y of the element would be this. This would be the y of the element, right? And if r is the radius, then realize that this is r sin theta. This is r sin theta. Yes or no? The y of the element is r sin theta. So this into r sin theta. So this is mi, mi into yi for the element. We need to sum up all the mi, yi's. Summing up all the mi, yi's is like saying integral this, where theta runs from 0 to pi, divided by the total mass, which is m. That's going to give me the y coordinate of the center of mass of this uniform semicircular wire. Right? Now, how could the wire have been non-uniform? If this lambda was not position independent, it was position dependent. Let's say if lambda was a function of theta, then this lambda could not have come out of the integral sign, right? Then you would have to incorporate it and then integrate it along with the rest of the terms. But in this case, in any case, we're talking of a uniform semicircular wire, so lambda would scoop out of the integral sign. So lambda r square by m integral sine theta d theta. Theta runs from 0 to pi, right? Which is like lambda r squared by m. Integral sine theta is minus cos theta. So it's like minus cos theta. Theta runs from 0 to pi. The value of minus cos theta at pi is plus 1. The value of minus cos theta at 0 is minus 1. So 1 minus minus 1, that is 2. It's going to give me 2, isn't it? When you supply the limits. No, Dhanraj, you're unsure about why this will be 2? Start from here. I'll explain everything again. Okay. See, did you realize that the y coordinate of the center of mass must lie along the y axis? Why? Because of symmetry. All right. Now, to be able to compute the y coordinate of the center of mass, what are we going to do? We'll break this up into several dm's, mass elements, right? Let's say this is a certain mass element, dm. For every mass element, we carry out a calculation of the following kind. Y of that mass element into dm. So, for every mass element located from this end to this end, we do a mass dm into the y, mass dm into y, plus mass dm into y for all the dm's, starting from theta equal to 0 to theta equal to pi, right? Now, what is this dm, this particular mass element? Look, what's the length of this element? R d theta. S is r theta, circumference. S is, I have a circle and there is a certain angle alpha here, then this length is going to be r alpha. If alpha is in radius, it's going to be r alpha, right? So if this angle is d theta, then this length is r d theta. I can explain why this is r d theta. Okay. And if this length is r d theta and lambda is the mass per unit length, then lambda into r d theta would be the mass dm of this element, right? Mass per unit length into length is going to give me the mass dm of the element. Lambda is the mass per unit length, as you can see, m by pi r, right? Into the y coordinate of this element. The y coordinate of this element is this length. This is r, so this is r sine theta. This is r, so this is r sine theta. So mi into yi, r sine theta, divided by the total mass. That makes it 2 lambda r squared by m, where lambda you can write as m by pi r, m by pi r. So if you write lambda as m by pi r, then this is like a 2r by pi. Right, a result that you want to remember. So if you have a semicircular wire, uniform semicircular wire, then its center of mass would lie at a distance 2r by pi as shown. That's the center of mass. Realize that 2 by pi is less than 1. So this is less than r. So this is r. So the center of mass will lie somewhere here, 2r by pi. Isn't it? So center of mass of a uniform semicircular wire will lie on the y-axis at 2r by pi. Got that? Now, no, just this one. You want to switch on the fan? Really? It's hot. I mean, I'm feeling all right, comfortable, neither hot nor cold. But when the fan is on, I'm not sure if my center of mass will stay put. Shall I continue? Okay, let's try out without the fan for a while, and if it gets really unbearable, then I'll compromise. Can I wrap this up? Hey, however, I want to address this in a different light. Even if you include this, hmm, even if you include this, then realize that the yi's are 0 for each of these, so they will not make a contribution. The mass elements here, suppose I include in the semicircular wire another wire, I connect another wire across the end. Will the center of mass change? No, because for if I have to include these mass elements, then the y for each of these mass elements is 0. So the contribution made by a mass element here, mi into 0, mi into 0, mi into 0 will be 0. The only thing that will vary is, it will not be at 2r by pi. The same computation, the total mass, it's not going to be m by pi r, it's going to be m by pi r plus 2r. Lambda will become different. Lambda will become different. Yes, that's why it gets shifted. No, you mean to say why I did not consider the y coordinate of the rod? Huh? That's because it was 0. That's because it was 0. Realize that in a rod, the reason I didn't look into the y is because all the y's were 0. See? This was the rod located entirely along the x-axis from 0 to L, right? So I computed the x coordinate of the center of mass in a manner that I suggested, right? Now if I look at a mass element here, dm, what's the y coordinate of this mass element? 0. So if I had to compute ycm, then that's going to be dm into y divided by integral dm. But all the y's are 0 for mass elements lying along the x-axis. So this would be 0 anyway. Got me? Now let me look at a semicircular disc. This was a semicircular wire. Now let me look at a semicircular disc. Now did I tell you in my last class that you could have a system in which there could be a bunch of continuous systems discretely placed. There could be several continuous systems. This is one continuous system, this is another continuous system, this is another continuous system. N continuous systems, but that are placed discretely. And if the mass of this is m1, and this continuous system would have its center of mass, let's say at r1. This is another continuous system, and the center of mass of this would be, let's say, at some r2. This is m3, its center of mass is at r3, and let's say this is some mn, and its center of mass is at rn. Did I not tell you that this system of continuous systems placed discretely would have its own center of mass? Center of mass of this collection would be RCM, which would be given by M1 R1 plus M2 R2 plus Mn Rn, where R1, R2, Rn are the center of mass of these respective entities divided by summation of Mi. That's how you get the center of mass of this discrete collection of continuous systems, right? Now, let me come back to the semicircular disc. Uniform semicircular disc, mass m and radius r. I hope you understand the difference between a disc and a wire, right? Disc and a wire, these are different things. Uniform semicircular disc, mass m radius r. Uniform semicircular disk, mass m and radius r. So now if it's a disk instead of a wire, then, and we're assuming obviously that it's of uniform thickness everywhere. It's of uniform, the disk is of uniform thickness everywhere. So then we talk of mass per unit area on the disk. We talk of mass per unit area on the disk, right? So mass per unit area on the disk sigma is going to be m divided by a half pi r square, is 2m by pi r square. That's the mass per unit area on the disk. Yes or no? Now, again, from symmetry considerations, let's say this was the x-axis and this was the y-axis. This was the center of the semicircular disk. Again, from symmetry considerations, can I not deduce that the center of mass of this disk will lie on the y-axis? Will lie on the y-axis. Not just that. Could I not imagine this disk? Could I not imagine this disk to be composed? Can I not imagine this disk to be composed of several rings placed end to end? This is a certain ring. This is a certain ring. The shaded area is a certain ring on the disk of radius, let's say, small r, and of thickness dr. Radius small r and of thickness dr. Is it? This is a ring. So can you not think of this disk to be composed of infinity of such semicircular rings where r runs from 0 to r equal to capital R, isn't it? You have several such rings placed end to end where r grows from 0 to capital R, where small r grows from 0 to capital R. Several such rings placed on top of each other, and to be able to include the entire disk, we make small r run continuously from 0 to capital R, so that all such semicircular rings get included in the summation wherever required. Are you okay with this? So let me look at one such ring. So in this one ring, radius r, it will have its own center of mass here. This entire ring could be replaced by a point mass placed here. What would this be? This ring would have its center of mass at 2r by pi, right? Like we figured out a little while ago, the center of mass of this ring would be at a distance 2r by pi. Small r is the radius of this ring, right? Now, what's the area of the shaded portion? What's the circumference of the shaded portion? Circumference of the shaded portion is pi r. Pi r is the circumference of the shaded portion, right? Into dr. Dr is the thickness. That will give me the area of the shaded portion. Pi r is the circumference into thickness. Dr will give me the area of the shaded portion, right? This area into mass per unit area, sigma, will give me the mass of the shaded portion. Area into mass per unit area will give me the mass of the shaded portion, right? So I have mass of this into the y of the center of mass of this. Y of the center of mass of this is 2r by pi. And we need to do a calculation of this kind for all the rings that constitute this disk and sum them up. That means we need to carry out the summation of this. That will give me the mi, where small r runs from 0 to capital R. Small r runs from 0 to capital R to be able to include every mass element prevalent upon the disk, right, divided by the total mass. The total mass is capital M. That will give me what? The y coordinate, the center of mass of the disk. This will give me the y coordinate of the center of mass of the disk. Yes or no? Right? Can you quickly carry out this calculation and tell me, put sigma equal to 2m by pi r squared and tell me how much it is? 4r by 3 pi, all right. 4r by 3 pi. That's the y coordinate of the center of mass of the disk. 4r by 3 pi, y coordinate of the center of mass of a uniform disk of radius r. 4r by 3 pi. So if I have a disk, then this disk could be replaced for the sake of applying Newton's second law by one single mass, capital M, placed at 4r by 3 pi. From the geometrical center along the line of symmetry. Are you okay with this? Huh? Okay, now that was the story of the semicircular disk. Let me look at a solid hemisphere of mass m and radius r. A solid hemisphere of mass m and radius r. Let's look into that process. Uniform solid hemisphere of mass m and radius r. So now when we're talking of a solid hemisphere, then we're talking of mass per unit volume, isn't it? We're then talking of mass per unit volume, that means the density, right? Volume density is what we're talking of. That means the volume density associated is going to be m by 2/3 pi r cube. That's mass per unit volume. Uniform solid hemisphere, mass m and radius r, m by 2/3 pi r cube. Yes or no? See, if I had a circular disk, not a semicircular disk, but I had a if I had a circular disk, uniform circular disk, where would its center of mass? At its center, at its geometrical center, right? Uniform circular disk would have its center of mass at its geometrical center from symmetry consideration. Huh? Yes, now, exactly, precise. Right. So, I would suggest that, well, the solid hemisphere is essentially several disks stacked over each other. There is a disk of radius capital R here and there is a disk of radius 0 here, right? So, this entire thing could be imagined to be composed of several disks stacked over each other. These are coaxial disks. This is the common axis of all the disks. This is the common axis of all the disks, several disks stacked over each other. Let's say this is a disk of radius small r, To constitute the solid hemisphere, small r would run from capital R to yes or no? Now, in any case, Let me look at one such disk. It's located at a distance y. One such disk, it's located at a distance y, and this is capital R, the radius of the hemisphere, and is of thickness dy, This particular circular disk is of radius small r and of thickness dy, right? Okay. What's the area of this disk? Pi into r squared is the area of this disk, right? Into the thickness dy, will it not give me the volume of the disk? The volume of this disk is area. ऊपर से देखेंगे तो we see a circular area which is pi r squared into the thickness dy. That's going to give me the volume of the disk. That's going to give me the volume of the sample disk. Volume of the disk, sample disk into the mass per unit volume density is going to give me the mass of the sample disk, shaded disk. And then the y coordinate of the center of mass, right? The center of mass of the disk would be at its geometrical center, which would be y, right? This is the mass into mi yi. Of this is going to be y. The y coordinate of the center of mass of the shaded portion would be at y. So this is mi yi. We need to sum up all the mi yi's. Sum up all the mi yi's. That can be done by this integration with limits being y equal to 0 to capital R. Y equal to 0 to capital R would include all the disks. Y equal to 0 to capital R would include all the disks that make up the hemisphere. Y equal to 0 would include the disk on the equatorial plane. Y equal to capital R would include the disk on the poles. Right? Yes or no? So y equal to 0 to capital R would include all the disks, and the appropriate summation of the mi yi's could be obtained. Divided by total mass. Divided by the total mass m. That's going to give me the y coordinate of the center of mass of the hemispherical disk. Y coordinate of the center of mass of the hemispherical disk. Hemisphere. Solid hemisphere. Not disk. The solid hemisphere. That's going to give me the y coordinate of the center of mass of the hemisphere. Uniform hemisphere. If you plug in rho equal to m by 2/3 pi r cube and do a calculation, this will turn out to be 3r by 8, which again is a result that you may want to remember. The y coordinate of the center of mass of a uniform solid hemisphere would be 3r by 8. When you plug in rho equal to blah blah blah, and by the way, this r squared would also have to be replaced. See, this r squared is really capital R squared minus y squared, which you will have to plug in so that you can integrate in terms of y. The subject of integration is y. So this small r squared is capital R squared. This small r squared is capital R squared minus y squared, which you will have to plug in here and carry out the appropriate integration. Clear? Is that all right? Next, we look into a solid cone of height, right circular cone of height h and radius capital R, mass m. Solid right circular cone of radius r and height h. This is a solid right circular cone ABC. This is the axis of the cone, so will give me the height and capital R is the radius of the cone. Solid right circular cone. Solid right circular cone. Mass M. So there is a volume density associated with it. Mass per unit volume. Rho then is like a M by 1/3 pi r square h. That's a mass per unit volume. That's the mass per unit volume. M by 1/3 pi r square h. Right? Now, what we can do for this solid cone is we can break up the cone into several discs. This is a certain disc. This is a certain disc of radius small r, located at a distance y from the apex and of thickness dy. This is one such disc. Do you realize that the right circular cone is actually composed of several such discs having a common axis, but different radii? At y equal to 0, small r is 0. At y equal to h, small r becomes, right? So when y runs from 0 to capital H, I'll be able to include all the discs that constitute the right circular cone, right? So the summation would have to be done keeping this in mind. Y equal to 0 to y equal to capital H would include all the constituent discs of this system, right? Okay, now this one disc. Again, from symmetry considerations, let's say this is the origin and let's say this is the y-axis. This is the y-axis. From symmetry, again, we can say that the y-coordinate of the center of mass of this must lie along the axis of the cone, right? So we need to come up with a summation of mi-yi's divided by the total mass. Mi-yi's divided by the total mass, right? So this is one mass. This is one mass element. What's the area of this disk? Pi r square. What's the thickness? Dy. That's the volume of the shaded portion. That's the volume of the shaded portion. Into density rho will give me the mass of the shaded portion. Into density rho will give me the mass of the shaded portion. So mass into y. I need a mass into y for all the disks. So mass into y, the y coordinate of this sample disk, right? And I need to carry out this for all the disks. I need to sum up all such things for this starting from y equal to 0 to y equal to capital H. A summation of all of this where y runs from 0 to capital H will give me like the summation mi-yi will give me like the summation mi-yi divided by the total mass. Will give me what? The y coordinate of the center of mass will give me the y coordinate of the center of mass. Now, what is the small r in terms of y? Realize that shopkeeper's method, दुकानदार का तरीका use करो. Find small r in terms of y. That's one of the things that you might want to use. Look, when the distance increases in this direction by h, the radius increases by capital R, right? That means increase in radius per unit distance that you travel in this direction is r by h. So over a distance y, the increase in radius would be this. From here to here, the radius increases by capital R. So increase in radius per unit distance in the y-axis is r by h. So for a distance y, the increase in radius would be small r, which will be this shopkeeper. दुकानदार का तरीका, एक चीज का दाम 10 रुपए है तो 10 चीज का दाम कितना रुपया होगा, वही किया है मैंने यहाँ पे. हाँ वही यार, यूनिटरी मतलब दुकानदार का तरीका, shopkeepers method. I mean, it's not stated as shopkeepers in your books. I mean, I chose to call it shopkeepers because दुकानदार ही तो यूज करता है unitary method, right? From A to D, the radius increases by capital R. Increase in radius per unit distance in the y direction is r by h, right? So for a change in distance y, this would be the increase in radius, so this must be small r. Otherwise, if you don't like it, if you're averse to this, then use similar triangles. This triangle is similar to this triangle. So small r by y is capital R by h. If you like it that way, I don't have a problem with that. Right? Similar triangles, ठीक है? क्यों बोल रहे हैं ये यूज करना चाहिए? पता है? Suppose there was a frustum of a cone. Why I want you to get mentally familiar with this? Actually, suppose there was a frustum. You understand what a frustum of a cone is, right? This radius is R1 and this radius is R2. Okay? This distance, say, is h. And you want to find the radius r at a distance y, suppose. Okay. So what you do is, from this to this, what's the increase in radius? R2 minus R1. Increase in radius per unit length is this. So increase in radius for a distance y would be this. This is the increase in radius from here to here. So if the increase is this much, the original was R1, then R1 plus the increase must be the radius here, smaller. You know what I'm doing here? From here to here, the increase in radius is R2 minus R1. So increase in radius per unit distance is R2 minus R1 by h. That's the increase per unit distance in this direction. So increase in radius over a distance y would be this into y. So from here to here, this is the increase in radius. And R1 was the original radius. So original radius plus the increase in radius would be the radius smaller. That would be the radius as a function of y. Radius as a function of y, the distance along this. Otherwise, in this case, you'll do like, you will complete a fictitious triangle here and then apply similar triangles, which is unnecessary. So that's why I said, sometimes Dukandar ka old fashioned tarika is the best tarika. Best thing to do, you know. So this is ordinary unitary method. I want you to understand this. Whether you like to use it or not, your choice, but you must understand what I've done here. So I've used exactly this. Right. So, and this is going to give me the y coordinate of the center of mass, where small r, like I said, is capital R by h into y. So you can plug in small r as capital R by h into y right here. Plug in rho equal to m by 1/3 pi r squared h, etc. And you're going to get the y coordinate of the center of mass of this, of the right circular cone, and it's going to turn out to be 3h by 4. It's going to turn out to be 3h by 4. And the center of mass, you know, will always give greater privilege to the portion of a distribution where there is greater mass, right? So obviously, you know, as you keep moving down, it becomes more and more massive down below, right? So the center of mass will be closer to the base, because that's going to give you a heavier mass distribution. The center of mass will be biased towards a heavier distribution, would have a propensity to be closer to the region in which there is greater mass, right? So that's why it's 3h by 4, it's greater than h by 2. So it will be further away from A and closer to the base, which is more massive, right? I mean, if there is a mass distribution, you know, a mass here, mass here, mass here, a mass here, and then you have some high density of mass here, Let's say all these masses were identical, but then if you had a system like this, you would expect the center of mass to be closer to this distribution than to these masses. That's something that you must physically understand. Okay? Okay. Now that we understand this, think of I hope you are all comfortable with things that I have communicated so far in the class today, right? Not a problem. Yeah, please ask. থাক অন থাক কোনো ব্যাপার নেই আমি জল নিয়ে আই answer for this. No, in the hemisphere, solid hemisphere. No, right? Let's say this wire. Yeah. What goes on till what end? What? This wire. No, I said this is the wire actually. I'm finding the center of mass of this semicircular wire. This is not included. So this has no role to play. This is only a line, geometrical line that is joining the two ends which I have used. This is just the diameter of this semicircular region. Huh? This wire. This wire has a length which is pi r, isn't it? Huh? Circumference of the wire will be the length of the wire. No. This was the actual wire. This was the actual wire, not the cross section. All right. Now, yet another important discussion in this context of computation of the center of mass. Let's say this is total mass m. This is a total mass m, continuous distribution, total mass m, right? And the center of mass of this capital M is here. Let's say, let me call it M1. The center of mass of this M1 is at R1, right? M1 is the total mass of a continuous distribution. M1 is the total mass of a continuous distribution, and R1 is the position vector of the center of mass above distribution. R1 is the center of mass of the above distribution, right? Now, from this distribution, I remove a certain mass. I cut a flesh out of it. Let's say the flesh that I cut out of this whole thing is a mass m2. This is the flesh that I remove out of this continuous distribution, and this flesh has mass m2. Right? This flesh has mass m2, and this flesh by itself, if you had isolated this flesh, then this flesh itself would have its own center of mass. This flesh by itself would have its own center of mass. Let's say the center of mass of this removed portion is at R2. Just this portion would have had its own center of mass, and let's say that's located at R2. Yes or no? Now, once I remove this, then the remaining portion would be a mass m1 minus m2. The remaining portion would be a mass m1 minus m2, right? I then want to venture into finding the center of mass of the rest of the portion, that is m1 minus m2, once I remove flesh m1, m2 from the larger mass m1. Now think of it like this. Let's say the mass m1 minus m2, that means other than this, when I remove this, then the remainder of the mass is m1 minus m2. Let's say the center of mass of m1 minus m2 is R. R is the center of mass of m1 minus m2. Whereas R2 is the center of mass of m2 alone. R1 minus R2 is the center of mass of m1 minus. So now, the entire mass, bigger mass m1, I want to compute R really. I have knowledge of R1, I have knowledge of R2. I want to see where the center of mass moves once m2 is cut out of the mill, right? Now imagine the following. It's as if I have a mass m1 minus m2. It's as if I have a mass m1 minus m2 located at R, right? R I want to know, and a mass m2 located at R2. It's as if I have a mass m1 minus m2. By the way, I'll just rearrange things. It will make sense that way. This would be R1, where I can imagine m1 to be placed. This is m2, and this is m1 minus m2, which is as if it's placed at. So it's as if I have a mass m2 placed at R2, a mass m1 minus m2 placed at R, which is the center of mass of m1 minus m2, and I have a mass m1 whose position vector is R. Yes or no? Look at just these two, m1 minus m2 and m2. The center of mass of m1 minus m2 is R. The center of mass of m2 is R2. Together, these two would have a center of mass, which would be the center of mass of m1 minus m2 plus m2, which is m1. Yes or no? m1 minus m2 has its center of mass at R. m2 has its center of mass at R2. So m1 minus m2 plus m2, which is the total mass, has its center of mass at R1. Now, what we learned a little while ago was the following. Beginning of the class, I reiterated a fact which I communicated in my last class, where I said R, the center of mass of this system and this system, R1, the center of mass of this system and this system is going to be m1 minus m2 into R plus m2 into R2 divided by m1 minus m2 plus m2, which is m1. Yes or no? If there is anyone who wants me to reiterate this fact, I have no issues doing so. You understood what I did here? Huh? So then, that's good. If I cross multiply, then essentially my objective is to be able to compute the position vector R of the center of mass of the remainder m1 minus m2. I want to know R. That's my objective, right? R then turns out to be m1 R1 minus m2 R2 by m1 minus m2. That's the position vector of this center of mass of the remaining portion. Sounds all right? Let's look at a few things, few illustrations around this. So, given a bigger mass, whose center of mass you know, out of which a small portion is removed, whose center of mass you know, you want to find the center of mass R of the remainder of the portion. Then this is what you do. M1 R1 minus the mass removed into the center of mass of the mass removed divided by M1 minus M2 mass of the remainder of the portion, right? Let's see how we generally carry out calculation for situations of this kind. So this is a circular disk of mass m and radius. Let's say this is a circular disk of mass m and radius r. The center of this disk would be here, and this would also be its center of mass. This would be the center of mass of capital M, right? From this disk, I remove a portion of radius r by 5. I remove a disk of radius r by 5. I remove a disk of radius r by 5. I then want to find the center of mass of the remainder of the disk. Clear? Now I'm coming to that also. C, let's say, is located at r by 3. C is let's say, located at r by 3 from O, the center of the bigger disk. Clear? Now, if the mass of the whole thing is capital M, what would be the mass of this? M by 25, right? Because the mass will be proportional to the area. This is actually 1/25th, the area of the whole thing. This is pi r squared by 25. This is pi r squared. So, mass will be proportional to the area, right? So, if the mass of this is M, the mass of this is M by 25. Right? Mass of this is going to be M by 25. Now, one thing again, even after removing this, let's say, call this the x direction, call this the x direction. Even after you remove this, do you realize that this body would exhibit symmetry about the x-axis? Would exhibit symmetry about the x-axis? So if it exhibits symmetry about the x-axis, there is no way to distinguish between regions above the x-axis and regions below the x-axis even after removal of this. So you would then expect the center of mass, to lie on the x-axis, to lie on the remaining portion, to lie on the x-axis. And now, again, from practical common sense, originally the center of mass of capital M was at O, right? Because there was equal mass distribution on either side of it. So it had to lie on O to show lack of bias towards the region to the right or left and top and bottom. But now if you remove this mass, then the portion to the right of O of the remaining becomes less heavy compared to the portion to the left of O. The left of O becomes heavier than the region to the right of O. So you would expect the center of mass to show proclivity towards the region to the left of O. So the new center of mass would get shifted somewhere here. You would expect the new center of mass to have got shifted to left of O, right? All right. What we do is, this is the bigger mass. And call this the origin. The x coordinate of this, so this is, let's say, x1 of this bigger mass, 0. This is x2 of the smaller mass, which is r by 3, right? The x coordinate of the remaining, x coordinate of the center of mass of the remaining. Original mass is m1, which is capital M, into the x coordinate of this mass, which would be 0, m1 x1, right? m1 into x1 minus mass of this, which would be m by 25, into the x coordinate of this. X coordinate of this is r by 3, divided by m1 minus m2, that is m minus m by 25, which is 24m by 25. So that makes it minus r by 72. That makes it minus r by 72. Minus r by 72 means, it's somewhere here. This is the positive direction of the x-axis. This is 0. Then this is x equal to minus r by 72. This will be minus r by 72, the x coordinate of the center of mass of the remainder of the portion once this is removed. Got me? I need to tell you, when I was in school, then my teachers in school taught us a concept, and that was way early, perhaps in class 8. They taught us a concept which was the moment of mass about a point. Not moment of force, but moment of mass about a point. And I'll quickly tell you that concept, and I think it comes in very handy. If I have a certain mass m, if I have a certain point mass m, and this is a certain point p, and let's say the position vector of A with respect to P is R. R is the position vector of A as seen by P. That's going to be position vector of A minus position vector of P. That's going to be R. Yes or no? R is going to be position vector of A minus position vector of P. That's going to be the vector AP. Right? Then the moment of the mass about P is m into r, Now, if I have a mass distribution, say m1, m2, m3, mn, and these masses are located at r1, r2, r3, rn, then what we have arrived at, and suppose this is the origin O, then this would be the vector r1, then m1 r1 would mean what? The moment of m1 about the origin. M2 r2 would mean what? The moment of m2 about the origin O, right? This is r2, this is r3, and so on and so forth, right? And this r of the center of mass, this is the center of mass, this is the r of the center of mass, which is like a point mass m1 plus m2 plus mn. Then the concept is, that's the understanding of center of mass. Center of mass is such a point where you can imagine all the mass to be concentrated such that the moment that this mass produces, about a certain point O is the sum of the moments produced by all other masses about O. Center of mass would be such a point such that the moment of the mass that it produces about O, which is going to be m1 plus m2 plus mn into RCM, that's a moment produced about O. That's the moment produced about O by the notional center of mass particle, right? That's going to be the vector sum of the moments produced by all the constituents, that is m1r1 plus m2r2 plus mnrn. Leading to RCM being moment of mass 1 about O, moment of mass 2 about O, moment of mass 3 about O divided by m1 plus m2 plus mn, right? Now, other thing that transpires here is, the following. Using this, can I get if I collect this term with m1 into RCM, if I collect this term with m2 into RCM and so on and so forth, then I end up getting m1 into R1 minus RCM plus m2 into R2 minus RCM plus mn into Rn minus RCM. That must be 0. Yes or no? Huh? Let's say there was one amongst these particles, the ith particle, whose mass was mi, whose position vector was ri. This was the center of mass particle. Whose position vector was RCM. Then, what would this vector be? Ri minus RCM, final position minus initial position. So this vector is like a Ri minus RCM, right? So then, what does Mi into Ri minus RCM mean? Moment of the ith mass about the center of mass. This is the moment of the ith mass about the center of mass by definition, right? Moment of the ith mass about the center of mass position, right? Moment of the first mass about the center of mass, moment of the second mass about the center of mass, moment of the third mass about the center of mass, moment of the nth mass about the center of mass. That means the vector sum of the moments of all masses about their center of mass will always be 0, The moment of all masses about the center of mass will be 0. Moments of all masses about the center of mass when added will turn out to be 0. The vector sum of the moments of all masses about the center of mass of that collection will always be 0. Now, in a one-dimensional scenario, you understand this concept, right? In a one-dimensional scenario, let's say there were two masses. A mass m1 and a mass m2. Now, in a one-dimensional scenario, let's say if there were two masses, then a mass on one side of the center of mass will be looked upon as producing a positive moment about the center of mass. The mass, all masses on the other side of the center of mass will produce a negative moment about the center of mass. What I really mean is, suppose the center of mass was the origin. Suppose the center of mass was the origin. You can always choose the center of mass to be the origin. Who stops you from doing that, right? And let's say this was the x-axis. This was the x-axis, right? Let's say the position was of m1 was x1, the position of m2 was, the coordinates of m2 were, the coordinate of m2 was x2. The x coordinate of m2 was x2. Evidently then, between x1 and x2, one of them is positive, the other one is negative. So then, what's the moment that m1 produces about O? m1 x1, which is positive. What's the moment that m2 produces about O? m2 x2, which is negative, because x2 is negative, as you can see, right? So, by convention, it's your choice. If you have a collection of particles on a straight line, if you have a collection of particles all lying along a straight line, then if center of mass is designated a certain position, if the center of mass is designated a certain position, then for all points on one side of the center of mass, allocate positive moments. For all points on the other side of the center of mass, allocate negative moments about the center of mass. Which means, suppose this distance is d1. Suppose this distance is d1. Then if I choose to have masses on this side produce positive moments about the center of mass, then the moment that m1 produces about O is going to be m1 d1, where d1 is a distance, so will always be positive. Now this is d2. The moment that m2 produces about the center of mass, the magnitude of the moment, d2 is the distance, so the magnitude of the moment that m2 produces about the center of mass is going to be m2 d2. But since it's on opposite side of m1, it will produce a negative moment about O. So the moment that m2, algebraic moment that m2 produces about O is going to be minus m2 d2. So this is the algebraic sum of the moments produced by m1 and m2 about the center of mass, and this must be and you could have had any number of masses, let's say along a straight line. This was a mass m1, this was mass m2, this was mass m3, and let's say if this was the center of mass, and if these distances were d1, d2, and these were positive distances d3, then realize that the moments produced about the center of mass m1 d1 plus m2 d2 minus m3 d3, right? If these produce positive moments, then this will produce a negative moment, minus m3 d3. That must be zero. Algebraic sum of the moments about the center of mass must always be. It's your choice whether you want to choose positive moments to be produced by these particles or those particles. The only thing is they must produce moments of opposite signs. Clear? And the algebraic sum of the moments about the center of mass must be necessarily zero. Got me? Now, having said this, suppose there was a L-shaped structure like this. This is length 2a. This is a. Obviously, this is also a. A. There was a laminar shape in the form of an L. There was a laminar, uniform laminar of mass M, shaped in the form of a L. So forget mass, whatever, but a uniform laminar shaped in the form of an L with its geometry given. And I want to find the center of mass of such a structure. I want to find the center of mass of such a structure. What we could do is, this structure could be looked upon as being produced out of removal of a mass from a 2a by 2a square. This is a square, 2a by 2a. And this square could have been broken up into forget this for a while. I just required for drawing this. The square could have been broken up into four squares, and I remove this square. I remove this square. I remove this square. Right? Then I'll get this L. Huh? If I remove this square, I'll get the L there. Right? Let's say for the 2a by 2a square, for the 2a by 2a square, if the mass is m, then what would be the mass of this a by a? M by 4, precise. It's going to be m by 4. So from a mass capital M, a mass m by 4 is removed. Right? Now, this is the diagonal of the bigger square. And portion which is removed, which is n by 4, that has its center of mass at the midpoint of this diagonal. At the midpoint of this, call it P, the center of mass of the removed portion lies. That is, it's as if m by 4 is concentrated at where this length you realize is a root 2, this length is a root 2. So then OP would be a root 2 by 2. Right? Hey, for the bigger square, the center of mass was lying here. Once you remove this mass, then this remainder of the portion becomes heavier. So you would expect the center of mass to shift here for the remaining portion, right? The remaining portion that is portion 3m by 4. The remaining portion has mass 3m by 4 will have its center of mass lie somewhere here at C1. Right? So 3m by 4 has its center of mass at C1. M by 4 has its center of mass at P. And the center of mass of 3m by 4 and m by 4 lies at O. Yes or no? The center of mass of m by 4 and 3m by 4 lies at. Are you there with me on this? नहीं क्या? नहीं समझ में आया ना पूरा? नहीं ना? बोलो. The center of the whole thing is like the center of mass of this 3m by 4 and m by 4, na? Which must be at O. 3m by 4 and m by 4 is the total mass. So the center of mass of this mass and this mass would be the center of mass of the whole thing, which is m. Right? So then I have like a mass m by 4 here and a mass 3m by 4 here. Right? And the center of mass of 3m by 4 and m by 4 is O. So do you realize that the moment that algebraic sum of the moments that m by 4 and 3m by 4 produce about their center of mass must be 0? So can I not say that m by 4 into OP, that's the moment that m by 4 produces about this? The moment that 3m by 4 produces about O is going to be minus 3m by 4 into C1O. That's the algebraic sum of the moments produced about the center of mass of 3m by 4 and m by 4. That is the center of mass of the whole thing. And this must be 0. This must be. And C1O is what we wanted to compute. The length C1O is what we wanted to compute. So OP we know is A root 2 by 2. So C1 can be obtained. C1O could be obtained readily. The center of mass of the remainder 3m by 4, which is now this L, which is this L. Are you okay with this? All right. This bit about the calculations related to center of mass, we can go endlessly, but then these are fundamentals. The rest would come out of problem solving. But the ideas are only these many when it comes to calculation of the position of the center of mass. But then now there are concepts related to the center of mass, and I don't want to dump it today upon you. One more thing, people have school on Saturday, so we will meet at our regular time at 4 o'clock. But then, even if we meet at our regular time 4 o'clock, we'll extend it for as long as we could perhaps manage. We'll keep our objectives a little open for our assembly on Saturday 4 o'clock. But then, by and large, it's going to be maths, and if time permits and if our energy levels permit, we will carry on with